Questions about anything? Just had a couple loose ends to clean up today. I'm going to tell you about the automorphism group of the unit disk. Those are the analytic functions that are one-to-one onto of the disk to itself. And now, of course, we know that such maps are conformal. So they're the conformal self-mappings of the unit disk. It's a very interesting group and very important in the subject of complex analysis. I also wanted to explain why we were calling that famous theorem the argument principle and what it has to do with the actual argument. So before I get rolling here, remember that in fact, the first problem in the first homework number 1, problem 1, you looked at these maps phi sub a of z. These are the famous Möbius transformations. 1 minus a bar z, where a was the point in the unit disk. These are called Möbius transformations. And basically, they turn out to be the one-to-one onto analytic self-maps of the unit disk. They're basically the automorphism group. They're with some little Schwarzlemma kind of no surprise. Okay, and so let's see, the homework problem 1 there, you showed that phi sub a mapped the unit disk to itself one-to-one and onto. And, of course, it's analytic. Okay. Well, the automorphism group of the unit disk, those are the set of, I'll call them capital phi, mappings that map the unit disk to the unit disk that are analytic and one-to-one onto. And fact number 1 is that that's a group. D10 is a group under composition. Okay, so obviously the identity map is in there because it's a one-to-one onto map of the disk to itself, and so that it has an identity element, and of course composition satisfies the group laws. The big question is, what is there an inverse in there? And now we know an important theorem that we didn't know until quite recently. Important reason. F, analytic and locally one-to-one, implies F prime is non-vanishing. And that guarantees that the inverse, so elements, so if phi is in the automorphism group, then so is phi inverse. Is analytic, and so also in the group. Questions about anything? Okay, so we couldn't start talking about this until we had that important fact. Of course, it doesn't have to be D10. We could be talking about a domain. And the Riemann mapping theorem, because of the Riemann mapping theorem, I can map any old simply connected domain with no holes one-to-one onto the unit disk by the Riemann mapping theorem. And so it means if you understand the automorphism group of the unit disk, you understand any simply connected domain because of the Riemann mapping theorem. Of course, the simply connected domain can't be the whole complex plane, but otherwise the Riemann mapping theorem gives you sort of an isomorphism between those groups. And that's a pretty important fact. A very interesting fact is that if domains have holes, then sometimes they don't have any automorphisms except the identity map. In fact, that's the norm. The automorphism group of the annulus is pretty interesting. There's lots of them in there, but not a whole lot. It's not as big a group as that group. Okay, so that's some fun things we'll talk about soon. So the theorem I want to tell you about, now that we're good and ready for it, the automorphism group of the unit disk is equal to lambda phi sub a, such that a is a constant in the unit disk and lambda is a unimodular constant. And the proof's going to be a snap. It's one of the reasons Schwartz proved his lemma. He needed it to study this thing. So the proof is, well, let's suppose capital phi is in there. Okay. Let's see. Well, then phi is 1-to-1 onto. So, and I want to think it's got to be some phi sub a. And remember, phi sub a maps a to 0. So, if I want to let a be the obvious thing, let's let a be the inverse image of 0, the origin. Okay. Now I got to think about a picture here. I'll draw a disk. Oh, let's see. At the moment, I only need 2 disks. There's the unit disk. Let's see. I'm going to map. Phi maps A to the origin. And I'm thinking Schwartz lemma. I got to use the Schwartz lemma somehow. And the Schwartz lemma applies to mappings from the unit disk to itself that preserve the origin. Okay? And I know a bunch of maps now. Problem number 1 there gave me a whole bunch of maps, and it's not hard to figure out a map that takes 0 to A. It's not Z minus A over the usual thing, but this map is Z. Remember, in that homework problem 1, you showed that the inverse of phi sub A is phi sub minus A. That maps 0 to A. And now when I make the composition, I'll call this one capital psi. That's going to be phi composed with phi sub minus A. So recall that problem 1. Part of the homework problem was to show that phi sub A inverse is equal to phi sub minus A. Okay, and so phi sub minus A is Z plus A. That's minus a minus A over 1 minus a minus is a plus, A bar Z. Okay, now I can use Schwartz lemma, and so I've got this. So the aha moment here is We know phi sub minus a is 1 to 1 onto, and capital phi is 1 to 1 onto, so phi is 1 to 1 onto. Analytic. And with that composition, phi of 0 is equal to 0. So Schwartz applies. Okay, so let's think Schwartz. What is Schwartz going to give me? Well, the most fun I ever had teaching 530 was the year that movie came out where they said it was a spoof on Star Wars, and they said, "Let the Schwartz be with you." Have you seen that one? It's probably kind of rare these days. Well, Schwartz tells you that, let's see, what the one that's going to be relevant is this one, line 2. So I call this B. Phi prime of 0 in modulus is less than or equal to 1. Okay, and if you think about that for a while, that's good to know. But it's actually equal to 1. I guess that's not the aha moment. This is maybe the aha moment. Phi inverse exists and is just like phi, because those things are 1 to 1 onto, and also satisfies that it fixes the origin. And so we can apply the same fact, namely that C inverse psi inverse prime of 0 is less than or equal to 1. But of course, psi inverse of prime by the inverse function theorem is 1 over psi prime at psi inverse. That's the inverse function theorem fact. And of course that's equal to 0. Phi inverse of 0 is 0. So I got that 1 over phi prime of 0 is also less than or equal to 1. So let's see, what does that imply? It implies that psi prime of 0 is greater than or equal to 1 in modulus when I take the inverse and change the direction of the inequality. And so I've got two things here. I'll put them in a box. This one, it's less than or equal to 1. This one, it's also greater than or equal to 1. So of course it's equal to 1. And this is why Schwartz part 2 is so important. We conclude that phi prime of 0 is equal to 1. And now Schwartz part 2 says that phi of z is a rotation. Phi of z equals lambda z for some unimodular constant. With modulus lambda equal 1. It kind of feels like, well, does that mean we're done? Let's see, what was phi? Phi was, psi was phi of phi, this is agony. These Greek letters always, let's see, that was phi sub minus a of z equals lambda z. Okay, so if I call this W, then of course we know the inverse. Let's see. Then if that's going to be W, then Z is going to be equal to phi sub minus A inverse of W. And phi sub minus A inverse is phi sub minus minus A. That's phi sub plus A. And so I get that capital phi of W is equal to lambda times Z, which is little phi sub A of W. So check. That's what I wanted to get. And so that's the proof. Questions about that?
I have a quick question. So the reason we can apply Schwartz limit to the inverse is because when we're doing the inverse function theorem, the space that it's applicable is where it's one-to-one, correct?
Let's see. The important fact was that if something is one-to-one, then its derivative is non-zero, which means the inverse is analytic. Okay. That was used when we showed that it was a group. So, if phi was one-to-one and onto an analytic, we know that its inverse is also the same. Yeah. An important fact that would carry over to all simply connected domains that aren't the whole complex plane is that the automorphism group of the unit disk is transitive. That's a word if you study geometric groups. Meaning, given any 2 points in the unit disk, A and B in the unit disk, there's a mapping in there that takes A to B. An automorphism. Did I say automorphism? Phi that takes A to B. So such that phi of A is equal to B. And because of the Riemann mapping theorem, that's true for any old simply connected domain that's not the whole complex plane. Of course, the whole complex plane also satisfies that because AZ plus B turns out to be the automorphism group of the whole complex plane. And it's quite different than this one. Of course, A could be equal to B because then the identity map would do that. So it doesn't matter if A is different than B. But the A different than B case is the interesting one to see. And the reason why is you'd have phi sub A and phi sub B both map 0 to the most. If you think about that, the first one maps A to 0. The second one maps B to 0. So, what do I could take. Let's see. I want to go backwards by the first one and forwards by the second one. So that would be phi. Let's see. That would be phi sub B composed with going backwards by A. And that's phi of minus A. Did we make note that the composition of two of those things is one of those things?
It's a group.
Oh, yeah, we did. So I managed to prove that without doing anything. It's a group. Yeah, so compositions of Möbius transformations are Möbius transformations up to multiplication by a constant. Kind of fun fact. What? I want to go... Oh, you're right. Oh. So what I want to do, phi sub negative b, because I want to take b... Are they both supposed to be negative? Let's see, I want to go a... What? A to 0, 0 to b. Okay. Yeah, that does it. Oops, sorry about that. If I'd been looking at my notes, I wouldn't have screwed that up. Questions about that? Okay, now I want to, this is kind of a fun thing to think about. The better you understand the complex log function, it takes a while to get the hang of it and look at it from several different angles. But this is one of the important ways of thinking about it. So now I'm going to shift over to the thing is called the argument principle. Okay, so something we know is that various branches of the log function satisfy e to the log of z is z. So however you cook up a log function, the logs are exactly defined to be such that when you go e to that thing, w log z, then you get z back. In fact, that sometimes I think of that as a set, and when I have a branch, I think of it as a function. Anyway, if that, when I'm thinking of it as an analytic function, then when you differentiate this, d by dz of e to the log z, I probably did this before, would be 1. And by the chain rule, that's e to the log z times d by dz of log z. And log of z, e to the log z is just z. So whatever branch of log you have, it always happens that the log is an antiderivative for z, 1 over z equals 1 over z, no matter what the branch. And the inspiration for this argument here d by dz of the log of f of z, if we can have a composition, would be 1 over f of z times f prime of z. And that's the thing that's in the argument principle function. Okay, so remember the picture for the argument principle. Let's suppose, so here's the picture. I've got, let's see, what's the picture? I've got a function that's analytic on a bigger set. Okay, so I had f that's analytic on this bigger set. And, okay, I'll call that a circle. And f prime is non-vanishing. So I got f is analytic inside. So it's analytic inside the orange circle. And it's non-vanishing on let's call this C for circle. Okay, and then remember that thing, I'll make it go around a couple times maybe. 1, 2, 3. Okay. It's non-vanishing, so that green thing doesn't hit 0. Okay, and this thing here, this curve is f of c. How many more arrows do I need? Like that. This one needs an arrow. Okay, that's the picture. And if I think of this, the inside, I've drawn this picture before. This inside gets mapped to the inside of this. Some points get hit more than others. Okay? That's the picture. Okay, and so here's the argument of why the argument principle, why it's called the argument principle. Let's think about a spot here, A, and a close by spot, B. Going, and I'm going to take a little piece of the curve here, like that. I'll call that little piece gamma going from A to B. That would get mapped over here somewhere. So this would be f of A and f of B. Okay, and that little piece would be f of gamma a to b. Well, I can calculate that integral from a to b in the argument principle if I had a branch of log that I can compose with. And so I would need if in this picture I would take a branch cut that goes out this way. Here's a branch cut. That'd be one of those alphas, and I'd take a log alpha that would give me exactly that branch cut for log. Then I could do the composition, at least on that little thing. Okay, so let's just do it. Now, the integral along that little segment from A to B of f prime over f dz, and remember from above, this f prime over f is d by dz of log of f by the chain rule. With that branch in particular, the branch there, and so the fundamental theorem of calculus would say that this is going to be log of f of b minus log of f of a. And let's see, that's equal to, the real part of the complex log is always that. But here we would have plus I times, and this is dependent on the branch I choose, so arg of f of b. And then minus the natural log of the modulus of f of a plus I times, and this would be an arg of f of a. Okay, so it turns out we're not going to care about these logs in the beginning. I'll explain why in a second. So let's put them out here by themselves. And I'll have plus I. An interesting thing happens here. This would be the increase in the argument. As you go from increase in the argument as, how would I write this? Increase in the argument as I go from A to B. And that is independent of the choice of the arg, of the branch. So that's the fascinating thing here. This purple thing is independent of the choice. Independent of choice of log. Of the branch. And that's fascinating. So that's true about that one little segment. If I went all the way around and added up a bunch of little segments, then something wonderful happens. Those first parts pairwise cancel. So this is a great thing. Add up the integrals along the segments using this fact. The real parts, those things in the... Okay, so I'm going to add up those little segments going all the way around. All the way around. Then the exciting thing is, then the log f of zk terms pairwise cancel. It's like a telescoping series. And of course, till you get to the very last one. And then the first one cancels the last one. They pairwise cancel, and the first one cancels the last one. So, when you go all the way around, what do you get? You get the integral around C of f prime over f dz. Let's see, the real parts cancel out, and we're going to get a sum. There's an I in front of it. I times the sum of the arguments. So delta arguments of f of z. Okay. And now if I divide both sides by 2 pi I, and I get equals 1 over 2 pi times the sum of the delta arguments. And of course, if you go around once, that's 2 pi. If you go around twice, that's 4 pi. So when I divide by 2 pi, that's the number of 2 times f winds around around 0, the origin, as z traces out the circle. So this is f of z, as z traces out the circle in the counterclockwise sense. So if you go back to that picture, I kind of like to think of have a watch on my wrist, and as I walk around, I look at f of z. F of z is not 0, so it's like a hand on a clock. And I watch it spin around. So every time it spins around, then I tick off a spin. Okay, so if I had a watch of a f of z, I'd watch it and add up those little increases as it goes around and around. And it's like if I was standing at the origin here, as a bug crawls around here, then f of z would crawl around here, and I'd stand at the origin and point at it. Every time I spin around, I'd add a thing on my watch. And so let's see. Yeah. So how many times does 0 get hit? I'd spin around. Well, let's see. This one, obviously, I'd spin around once. I'd come back here and hit it. And then I'd start looking at this one, and it would spin around again. And then it would spin around a third time. So I'd spin around 3 times. That means the origin gets hit 3 times. It could be hit with multiplicity, remember. So how do you get? You could either get hit 3 times by a 0 of order 3, or a simple 0 and a 0 of order 2, or 3 simple zeros. And those could be possible. But the argument principle gives me a very almost numerical way of calculating that. Okay. And if I replace remember the trick of if I put f of z minus w in the denominator, then it tells me how many times w gets hit. Okay, and if you do the same routine here, you would see that everything in here gets hit 3 times. Everything in here gets hit twice. Everything in here gets hit exactly once. So that'd be simple zeros. And everything out here doesn't get hit at all. Anyway, there's a very physical way of thinking about that integral. Not on the curve. The green thing doesn't go because it's non-zero on the curve. But inside, then the yellow stuff, so if you think about where 0 would maybe hit, if they were simple zeros, there'd be 3 of them in here. There could be 2, there could be 1 double 0 and 1 single, or there could be just 1 triple 0. But those would be the points that hit 0. So if I say a W in here, it gets hit twice inside C.
I have a quick question.
Yeah.
So will the actual curve be hit multiple times, or are those hit once?
Well, the only things that get hit with multiplicity are where they cross. But the argument principle pertains to the mapping on the inside of the circle. So it doesn't tell you anything about what happens on the circle. Usually when we're dealing in complex analysis, we have a curve that has non-vanishing derivatives, so it's not going to have any weird kinks or anything. I mean, I guess if you have piecewise C1s, it could have kinks, but it's not too weird at least. Yeah?
And the image curve should be sort of convex.
Well, that's the weird thing. It appears to have to be counterclockwise. If it goes the other way, then that increase in argument would be positive, and that could only happen if there's poles. So it does give you some geometric facts about what the image curve could look like, which are kind of interesting. That follows from conformality, and we'll talk about that later on when we do conformal mapping. Anyway, so let's see, I should do another little fact. So remark, apply the same reasoning. F of z equals, capital F of z equals f of z minus w. Then you get 1 over 2 pi I integral around c. Capital F prime would be little f prime, and so it would look like this integral. And that's equal to the number of times f of z wraps around w. F of c wraps around w. And that's equal to, by what we proved earlier, the total number of zeros of f of z minus w inside C, important to say, counted with multiplicity. Let's see.
Excuse me.
Yeah.
I have one kind of quick question.
Okay.
Does C necessarily have to be a circle, or does that just make the
Now, the same picture would work for something more exotic, yeah. But we're not thinking about those exotic things just yet. We get a lot of mileage out of knowing it on the circle, as you've been seeing. We get an open mapping theorem and all kinds of things just pop out from the circle case. Let's see. Here's an important calculation. Let's do the example. F of z equals z. Let's see. Oh, here's what I want to do up here. Here's an important calculation. Let's suppose I have C parametrized by z of t. Or maybe let's call it gamma instead of C. A less than or equal to t less than or equal to b. Then the image of gamma would be parametrized by f of z of t. And if I calculate one over 2 pi I integral around gamma of f prime of z over f of z dz, that stands for integral from a to b of f prime of z of t over f of z of t. Let's say I want a minus w on the bottom here. F of z of t minus w. And now remember, this dz stands for z prime of t dt. And I've shown you this before. This is one of our chain rules. And so that's equal to 1 over 2 pi I integral from a to b of d by dz, d by dt of f of z of t. Of course, we have that parameterization down here. And that's what I'm calling 1 over 2 pi I integral around the curve f of gamma. Let's see, on the top, that's the z prime of t dt. And on the bottom, we would have a zeta minus w and we'll have a d 1, and this is a d zeta. And that's called the winding number of the curve about the point W. Okay, and that's called the index of the curve about W, or the winding number. Of f of omega about W. And that's equal to the number of times f of gamma winds around W in the counterclockwise sense. I guess this is a good. There's an old qualifier exam question that's fun to think about. A qual problem. How many zeros? This was a qual question in the year 2001. How many zeros of that polynomial fall in the first quadrant? And it's a fascinating thing to think about, because if you can figure it out, it means you understand the argument principle from all possible angles. But you have to think of, so let's see, if you're going to use the argument principle, you would have to do these things on a curve that looks like a quarter piece of pizza. Here, this would go from 0 to r along the real axis. This would be I times r. And when you look at the increase in argument along all the three different pieces of the boundary, let's see, of course, r, you take r big enough so that all the zeros there are going to be are in there, using the fundamental theorem of algebra. So r would need to be bigger than something. But it's easy to figure out the increase of the argument along the real line is 0. You can figure out what it is along the imaginary axis there. But then to figure out what it is along the circular part, you need to calculate the integral of f prime over f and let r go to infinity using basic estimates for integrals. Okay, so the interesting one to think. This side is a very easy. Delta r is extremely easy. It's 0. Easiest. This one's it's easy. Delta arg is easy. But you have to think about it. That's because that maps that little green line into the upper half plane. And so, of course, you can use the principal argument to figure out the increase in the argument. So you just have to think about it a little bit, and it pops right out. And this one is interesting. You take a limit of the imaginary part. That's an important thing if you understand that argument above. You throw away the real part, so you only care about the imaginary part. So you take the limit of the imaginary part of the integral along that circular part. Let's call this c sub r of f prime would be 2001 z to the 2000 plus 1999 over z to the 2001 plus